Okay, so let's chit chat about the assignment from yesterday and when it's absolutely necessary that you convert like atmospheres into pascals. The only time it is absolutely spot necessary is when you get into a question like number 7. So like on number 7, you've got what's the volume, 0.2 moles of oxygen, okay, whatever it is. So when you're dealing with just the PV equaling nRT, okay? So if you're just dealing with one equation like this, where you're going to solve for pressure, volume, whatever that is, and this is like the quintessential, it has to be in, pressure has to be in newtons per square meter, the volume has to be in cubic meters, the temperature has to be in Kelvin, because that's the only way the units can work out. Now, in contrast to that, when you get to a question like on number 9. So number 9, you're dealing with a ratio, okay? So on number 9, you're saying, oh, hey, here's the pressure, here's the temperature. So if you look on number 9, Alex, let me see the paper. The blue paper. So on number 9, you got 2 atmospheres, temperature 20 degrees Celsius, which is about what we're at right now. Then it says, what's going to be the new pressure if the temperature is raised to 40, okay? Well, here's the deal. Just think this through. Remember, temperature is a measure of, like, it's a speedometer. It tells you how fast the particles are moving. If you like the Timmy analogy, it tells you how many Skittles Timmy has. So, if you raise the temperature to 40, did you give the kids Skittles or take Skittles away? Scooter. Did we give them caffeine or take caffeine away? Yeah. We raised the temperature. So if you look at that combined gas law, PV V1 over T1 equaling P2 V2 over T2. So in this situation, you're assuming that the volumes of the tire stayed the same. You have to, because you weren't given any information about how the volumes of the tire changed, okay?
Yes.
So you just have to assume that that volume is going to remain constant, okay? Because you weren't given any information about that. So then you go, okay, P1, because I hate fractions, and P2 times T1. Now, if you think about this at all, you go, well, the temperature is going to go up, right? I'm going to give the second graders more energy. I'm going to give them more Skittles. I'm going to have more collisions with my ankle biters from the little rugrats. My pressure is going to go up because I'm going to have more collisions with the little kids, right?
He says ratio.
So then you go, okay, well, that's P1 times T2 over T1. Now, at this point, let's say you have no idea of gas laws, you don't know anything, you go, man, I don't know which temperature to put where. Well, first off, can you leave the temperature in Celsius? Absolutely not. This temperature has to be in Kelvin. You cannot work on 40 and 20, okay? You have to work in Kelvin because that's what atoms feel. So then the question being, you got the 2 temperatures. So one option is that you can put the 293 on top and the 313 on the bottom. That's an option. Now, contrast. If I take a pressure and multiply it by 293 over 313, is my new pressure going to be bigger or smaller than my initial one?
Smaller.
Smaller. So right away, if you do this, you go, oh, this is a train wreck. Because you're saying that I'm going to increase the temperature, I'm going to give the kids more Skittles, but yet the pressure is going to drop, which doesn't make any sense at all. But then if you go, oh, let's put that 313 on top and 293 on the bottom, now I'm multiplying by a factor bigger than 1, hey, I'm going to get a bigger pressure. So on number 9, you can either leave the atmospheres, or if you're hardcore, it's like me at Burkamp, I was president of the Pascal Club in high school. I'm going to work in newtons per square meter. Cool. Put them in newtons per square meter.
Doesn't matter.
Because I've got both answers. So on number 9, if you left it in atmospheres, both of them, oddly enough, should be around 2. Okay? Cool with that. Make sure on number 11 that you have 2 answers to number 11. You need the new length of the iron, and you need the change in the length of the iron in centimeters. Okay? So you should have 2 answers on number 9. Excuse me, on number 11. The new length, which should be a little bit bigger than 50, and then the change in length in centimeters. When you get to number 13 and 14, you're talking about the changes in volume and the changes in area.
Yeah.
I have those equations on the bottom of that list of coefficients. So, like, you've got area naught
I just didn't use
equaling 1 plus 2 alpha delta T. So that alpha is that coefficient of thermal expansion. You just have to look on the paper and find it. Now, in terms of that area naught value, I don't care what you leave it in. If you want to leave that in centimeters, cool, leave it in centimeters. It doesn't make any difference. If you want to convert it into meters, do it that way, that's great. Okay, I don't care. Personally, I just leave it in centimeters because it makes the math a little bit simpler. Okay, doesn't make any difference. But no matter what, on 13, your first digit should be a 1, and 14, your first digit should be a 3. Okay?
Can you tell us what the exponent should be on the?
It depends upon if you're in square
centimeters.
meters or square centimeters.
Let's do square centimeters.
On which one?
13 and 14. Well,
Oh,
keep it on
okay,
14.
never mind, I
Keep it on
understand now. It's okay.
It's all
I was
good.
confused why we had different ones, but I realized he's in centimeters and I'm in meters. I was like, that makes sense.
14. Yeah.
That would explain it.
So we got the same thing.
Yeah.
I like how this played into it. I'm not sure how that was part of it, but it was.
It means
Okay.
or something.
So let's talk about number 19.
Yes.
So on number 19, and you'll once I got to run off a second set of equation sheets for AP Physics 2 because this is where this is. But I'm just going to kind of give you this equation for now. But it's delta Q over unit of time equals K A delta T over L. So let me explain how this will at some point impact your lives, okay? At some point, you're going to be in control of the thermostat on your house, okay? At some point, you will have that power, okay? It's like, oh, I have the power of the thermostat.
No, you can just have flexibility.
So what this is why this will impact your life. This equation impacts your life. So L is the thickness of the wall. When you move into your house, you really can't change the thickness of your wall. That's kind of a set value, okay? Area is the cross-sectional area of the wall. Really can't change that either. It's kind of a fixed value, okay? K is the rate at which, it's a constant based upon different materials. So if you look on page 385, some of these have very, very high coefficients, others have very, very low. So like on number 19 on that question, if you look that up, concrete has a value of 0.8, and it gets wonky because it's like watts meters squared over Kelvin or Celsius. And then wood is 0.2, same thing. So that's that value of K. So here's the basic idea. The bigger this number is for that value of lowercase k, the more energy that it transfers through, okay? So what you can control, you can't control the thickness of the walls on your house. you can't control what the walls are made of unless you add more insulation. You can't control the area. What you can control is the temperature gradient between the inside of the house and the outside of the house. That's what you have control over. Now, in what season do you think there's a bigger temperature gradient? In summer, between the outside temperature and the inside temperature of your house, or in winter, between the inside temperature and the outside temperature? Winter, why?
It's really cold outside, and I don't want it to be really cold inside.
Okay, so in winter, like if you're in Fahrenheit, you might want the inside of your house to be 70 degrees. It's a blizzard, the outside temperature might be 10, okay? So that's a big temperature difference. So here's what's going to be important. This is in joules per second. So the bigger that temperature is, the bigger that gap is between the inside and the outside, the more energy that you lose per unit of time. Okay, in terms of the sun, in terms of winter, that's a reflection of how much energy is passing through your house, your walls, per unit of time. So you go, ooh, I want it warm inside. I crank that temperature up to 70. Cool, nice. And it's 10 degrees outside. That's a big temperature gradient, which means you're going to lose a lot of energy. So this is where it becomes what we call a negative feedback loop. So the warmer you try and keep the house, the more energy that you lose per unit of time. Guess what? It's joules per second. So, well, maybe I can put on a sweater and I can drop that temperature down to 60. Well, if you drop that inside temperature down to 60, now you have a smaller temperature gradient, which means you're losing less energy per unit of time, and it's actually then easier to keep your house warm because you're not losing as much energy per unit of time. Okay? Same thing is true in the summer. Hey, I want to cool the house down to 65 versus 72. Well, if you try and cool your house down to 65, that's a big temperature gradient. You're going to lose a lot of energy per unit of time. Alex.
So for question 11, I think you forgot to tell everyone that you need to also have the final length in there, because I only see what will
number
be
11?
Yeah, what will
You calculate the final length, Alex.
Oh wait. Oh no, it's the push start.
I gave you the original length, you
What will
calculate
be
the new
final
length.
length that I need to change?
I gave you L naught.
Ice for Gore.
Now, so if you look on question number 19, so you've got a concrete wall that's 20 centimeters thick, okay? And you know that Q over time is Ka delta T over L is your thickness. So both walls are going to have the same area, not a factor. The change in temperature is going to be the same for both, okay? So the only thing that you can mess with is that value of K and L, which is the thickness. So if you compare these two values, concrete has a value of 0.8, wood has a value of 0.2, okay? So those are your two potential values. So this is 20 centimeters. So you want the same rate of thermal flow. So this is 20, so if you look at the ratio of 0.8 to 0.2, which is a value of 4. So mathematically, you only have two options. Either you make that wall made out of wood 4 times thicker, and you make it 80 centimeters, which would be about like yay, okay? Or you divide it by a factor of 4 and make it 5 centimeters, which would be about like yay. Okay? Those are your two options. So on number 19, your answer is either 80 centimeters or 5 centimeters. And no, I'm not going to give you around what the answer is going to be. What,
It's
Chuck?
either- It's one or the other?
It's one or the other.
Uh-oh.
It's either 80 or it's 5.
He got
It's
80.
either 4 times thicker or 1/4 as much.
No, I hate
That wall.
No, because
You see, he got 80.
Chuck, set it up as a ratio.
I think I did.
You want the same Q over T's, right?
Okay, so that's what I didn't do. I set it up the other way.
You want the same Q over T's, because you want the same energy exchange.
Yeah, I set it up as Q times T.
I just made my own equation.
How'd that work for you?
Well, it got me one
That's
answer.
what I
Yeah, that's
did.
good.
A wrong answer.
It got me one of the answers.
You make
Okay.
your own equation.
So
Okay, anything else on that assignment?
King of the.
Going once, going twice?
yeah.
So,
Okay.
so, get that handed in.
L Charles.
Stop that, I gotta go heat up water.